G'day everyone. Today we're going to continue looking at the concept design of our robot and how to simulate it in Gazebo. By the end of this video, you're going to have a 3D simulated version of your robot that you can drive around a virtual room, and I think that's pretty cool, so let's get straight to it. We're going to pick straight up from the end of the last tutorial where we were making our URDF file, so if you haven't seen that one yet, you're going to want to go ahead and watch that first. I'd also highly recommend that you watch my other tutorial that has an overview of Gazebo and how it integrates with ROS. I'll include a link in the description and up in the corner. We're going to start by dropping our robot with the URDF that we've made into Gazebo as it is right now, and then from there we'll work to improve it and get the simulation going the way we want it. This first bit is going to consist of 3 steps. Firstly, we're going to be running Robot State Publisher just like we were before, only now we'll be running it in simulation mode. Secondly, we'll be launching Gazebo with ROS compatibility enabled. And thirdly, we'll be running the Gazebo robot spawner script to spawn our robot into the Gazebo environment. To launch Robot State Publisher, we're going to do pretty much exactly what we did last time, only this time we're also going to set the use sim time parameter to true. Whenever we're working with Gazebo and simulations, it's important that when we run other nodes that we enable use sim time, and that tells those nodes to keep their clock, their timing synchronized with Gazebo. And if we don't do that, things will get out of sync. And so that goes for Robot State Publisher as well, whether we're launching it, whether we're running it by itself or whether we're launching it as part of a launch file. And so the launch file that we used last time, it exposes this parameter for us. So we'll get back into our workspace and source it. Now last time we were launching it like this. All we've got to do is add to the end use sim time equals true. And now this will launch Robot State Publisher with sim time enabled. Next we need to launch Gazebo, and to do that we're going to use the launch file provided by the Gazebo ROS package. If you haven't already installed Gazebo, you can do that with the command I'll put up on the screen now, and then open a new terminal and we'll type ROS2 launch Gazebo ROS gazebo.launch.py. And so this should start up Gazebo. And it's there, we've got an empty Gazebo window. Finally, we can spawn our robot using the spawn script that's also provided by the Gazebo ROS package. So to do that, we'll type ROS2 run Gazebo ROS spawn entity.py, and we'll type -topic robot description. So that tells it that the URDF is being published by Robot State Publisher on a topic called robot description. And we'll type entity, and then we've got to give it a name. I'm just going to type bot name. This doesn't really matter. And then what that'll do is that'll spawn a copy of our robot here in the Gazebo window. The colors don't look quite right and we can't drive it around just yet. We'll fix that soon. Now, before we really start to work on this, we're going to do one more thing that'll make our lives a bit easier. Instead of having to close and rerun all 3 of these programs every time we make a change, we're going to wrap them all up into a single launch file that we can just start and stop. Now this file is a little bit complicated to write from scratch, so I'm going to include a link in the description to one that you can download, but if you want you can copy and type in mine as you see it on the screen. For me, I'm just going to make mine magically appear here in the launch directory. So you can see here it's called launchsim.launch.py. And I'm just going to quickly go over the things that are in this file. So we start off, we've got a bunch of imports. They're just there to make the Python code simpler. Now, first up, we include the Robot State Publisher launch file that we were using last time. So we can see the package name here. Now, I've got robot testing there. We want this to be the name of our package. So for me, it's Articubot1. Then you can see here it launches our rsp.launch.py and it forces the use sim time parameter to be true. So that's what we want. Then next up, we include the Gazebo launch file. So it's Gazebo ROS is the package, and then the Gazebo launch file there. And then finally, we've got the spawn entity script from the Gazebo ROS package as well that we had before with the robot description and a name for it. And it tells it to just do all of those things. So now that we've got that, what I'm going to do is I will rerun Colcon to rebuild it. Now we want to make sure that we've closed everything from before. So make sure we'll quit that one and quit that one. And now we can go ROS2 launch Articubot1 launch sim.launch.py. You can see it's going to start robot state publisher and gazebo and spawn our robot. So it's exactly what we had before, but now we only have to run that one command to do it. And remember also that whenever we close gazebo, we've got to make sure we remember to manually hit Control-C to stop the launch file. So now that we can relaunch our simulation nice and quickly, let's get to work improving it. As I mentioned in the gazebo overview tutorial, we can expand on our URDF by adding gazebo tags, which let us tell gazebo certain things that it can do when it simulates. And we also saw in that video that the first thing we can tackle is fixing up the colors. So we'll open up our robotcore.exacro file from last time. And then for every link that has a visual tag, we want to add a gazebo tag where we specify the color. So I'll start off here with the chassis link. So we'll add gazebo reference equals chassis. And now here we want to set the material to gazebo white. And now I'll go ahead and do the other ones as well. So now if we go and relaunch gazebo, we can see we've got our white chassis, our blue wheels, and our black caster wheel, just like we want. So now that we've got our colors sorted out, it's time for the fun bit, driving it around. Before we start doing the work to get our robot driving, there are a couple of concepts we should take a moment to cover. The first thing to note is that later on in the project, we'll be using the fantastic ROS2 control library to handle our control code. What's cool about that is the same code will work for both the simulated robot and the real robot, which minimizes the differences between the two. And when we do that, I'll also go through these concepts in much more depth. But since ROS2 control is a bit complicated to set up, today we're just going to use a more simple differential drive control system that comes with Gazebo. It'll do fine for the next while, and we'll also just do a brief overview of the concepts. When we have a real robot, it'll have a control system. The main thing that control system does is take a command velocity input, that's how fast we want the robot to be going. It'll translate that into motor commands for the motor drivers. It'll read the actual motor speeds back out and calculate the true velocity. With ROS, that command velocity is on a topic called cmd_vel, and the type is twist, which is just 6 numbers: linear velocity in the x, y, and z axes, and angular velocity around each axis. For a differential drive robot though, we can only control 2 axes. We've got linear speed in x, so that's driving forwards and backwards, and angular speed in z, that's turning. And so the other 4 numbers will always just be 0. Rather than the true velocity, we're often more interested in the robot's position. The control system can estimate this for us by integrating the velocity over time, adding it up in tiny little time steps. This process is called dead reckoning, and the resulting position estimate is called our odometry. In the Gazebo overview tutorial, we saw that whenever we want to use ROS to interact with Gazebo, we do it with plugins. The control system will be a plugin, ROS2 control, or for today, Gazebo ROS diff drive, and that will interact with the core Gazebo code, which is simulating all the motors and stuff. And this whole system then interacts with our diagram from the last video. Instead of faking the joint states with Joint State Publisher GUI, the Gazebo robot is spawned from the robot description, and the joint states are published by the control plugin. The plugin also broadcasts a transform from a new frame called ODOM, and that frame is kind of like the world origin, it's the robot's start position. So it broadcasts the transform from ODOM to baselink, and that lets us know the current position estimate for our robot. The plugin we're using today though doesn't quite follow this. Instead of publishing the joint states, it just publishes the left and right wheel transforms directly, which has the same effect overall. So to drive our robot around, we're going to need to add a control plugin. Now, rather than adding more and more things into this core Xacro file, what we're going to do is we're going to add a new include file here that's going to contain the information for the gazebo control. So we'll type Xacro include file name gazebo control. And then this file doesn't exist right now, so we better create it. And we'll start off by grabbing this just so that we can get the XML header and the robot tag set up. And now in here, we're just going to have a gazebo tag. Oop, just tell it it's an XML file. And then inside our gazebo tag, we're going to have a plugin tag. And then in the plugin tag at the top, we're going to need to specify a name. This doesn't matter too much, so we'll just go diff drive and then a file name. And the file name here is the file name of the plugin that we're using. And the one we're going to use today is called lib gazebo ross diffdrive.so. Now in here, we're going to put all of the settings that the plugin needs. There's a whole bunch of them. I'm going to step through them and you can just copy what I do. So we'll start, I'll put some comments with the wheel information. So we have to specify the left joint. And our left wheel joint is called left wheel joint. Then we have to do the same for the right wheel. So we'll just change all of these to right. We have to specify the wheel separation. And in this case, for mine, it was 0.35. If you remember here with our left and right wheels, they were 0.175 away from the center. So we double that is separation of 0.35. And our wheel diameter was 0.1 meters. So that's the wheel information. It's important that you get those ones correct for your robot. Then we've got the limits. So this is acceleration and torque limits. So we'll go max wheel torque. We're just going to set these to be pretty big. It doesn't matter too much what we do. You can tweak them to make your simulation behave the way you want if you like. Acceleration. We'll make this 10. And then finally output. This just tells the plugin exactly what it needs to output. Just copy what I do here. So we've got odometry frame is called odom. Whoop. The robot base frame. Now our base frame was called base link, as it's according to the standard. Then we've got publish odom. Should it publish the odometry to a message? And we'll say true. Publish odom tf. Do we want it to publish the odometry transform? Yes, we want it to do that. And publish wheel transform. Do we want it to do that? And yes, we also want it to do that. So that is the differential drive plugin all configured and ready to go. So now let's test it. I've just realized I forgot an underscore here, so make sure you put that in there. So now we'll reopen our terminal, make sure we rebuild, head back to here, kill the old gazebo if it's still running, and then we'll launch it again. And so we can see our robot is just sitting there like it was before, but now it's waiting for us to send command velocities. So what we'll do is we'll open a new tab, and the easiest way for us to get started sending command velocities is to use a program called Teleop Twist Keyboard. So we'll type ROS2 run Teleop Twist Keyboard. And what that means, teleop is short for teleoperation, which is remote controlled by an operator, by a human operator, as opposed to autonomous control. Twist is the type of message that ROS uses to express linear and angular velocities together, and keyboard because we're using our keyboard. So teleop twist keyboard means using our keyboard to remotely send velocities to the robot. So we'll run that. Now this program is a bit annoying. It only works if you have it open as the active window. So I'll move it over here. We'll have our robot there, and then I'll have this as the active window. And it says here that to drive it around, we use U, I, O, J, K, L, M, comma, and full stop. So I'm going to start by pressing I, and hopefully our robot's going to move. And we'll see it does move, but it's jumping around. And the reason for that is because if you recall in the last video, when we made our URDF, we said that our caster wheel was going to be frictionless, but we haven't made it frictionless yet. And so that wheel's kind of dragging along the ground and causing it to kick up. So we better fix that. We'll go back to our robot core.exacro and we'll find our caster wheel link and the Gazebo reference for it. And what we can do is Gazebo lets us specify the friction coefficient. Now, the way we do that is we go mu1 value. Now you can set it to 0. I like to just set it to a very small value just in case there's like a divide by 0 somewhere. And you actually have to set mu1 and mu2. They're two slightly different friction coefficients. So we'll do that. We'll close Gazebo. And then we'll rerun it. And hopefully now when we drive around, it'll be nice and smooth and we can steer and drive around. Now this whole keyboard thing is pretty annoying because often you'll go, oh, I want to zoom in on the robot, and then now it's running away and I'm typing and it's not doing anything because I've got to get this open. And so instead, it's much easier to use a joystick and use Teleop Twist Joy along with the Joy node from the Joy package. We'll look more closely at that in a later tutorial, but if you want to explore that now, I would recommend it if you've got a controller handy. It makes it much easier because even when that window is not active, you can control it with the controller. So we've got a simulation going. It's a bit rough, but it'll do for now. What we'd also like to be able to do is use RViz to visualize what it thinks is going on with the robot. So I'm going to open up a new tab. We'll launch RViz. We'll add a transform. And we'll set our fixed frame to ODOM. So that's telling us where the robot is with respect to Gazebo's origin. We'll also add our robot model and set the topic. And so now, let's see if we can show all of this at once. Now, as we drive our robot around, we should see it moving in Gazebo, and Gazebo is then reporting the robot's position. It's publishing the odometry messages and transforms, and RViz is then seeing them and displaying to us what it thinks the robot is doing. So here Gazebo is kind of pretending to be the real world, some robot that we've physically got driving around the room, and RViz is how we would normally be monitoring that robot from our computer. So as we drive the robot around in Gazebo, we can see where it is in RViz because the plugin is publishing the transform from the ODOM frame to the baselink frame. Now, the last thing I'm going to do here in RViz is to just save this config in case we want to use it again. So just like last time, I'm just going to put it in this config directory, and I'm going to call this one drivebot.rviz. And that way, if we want to do that again later, we can bring it back up. Now, the last thing I'm going to do before we finish is quickly make a world for our robot to drive around in. This world we've got at the moment is pretty boring, just a big grey plane. So I'm going to build a quick obstacle course and show you how to launch that. I covered this in the Gazebo tutorial, so I'm going to run through this pretty quickly. If you want more details, you can check that out there. So I'm going to save this world, and where I'm going to save it to is here in our package directory. We've got a worlds directory, so I'm going to call it obstacles.world. Hit save. Oop, I meant to delete the robot before we did that, otherwise the robot will be in our world. So I'll just delete the robot, hit save again, save over the top of the old one. So now we'll close that. And now next time when we launch this, what we can do is we can add world is, and then we'll just do the relative path to where it is. So from where we are in our workspace, it's source / articubot1 / worlds / obstacles.world. And now when we launch Gazebo, what it should do is it should launch it with that world file and spawn our robot right in there, ready to drive around. And you can have a go at trying to navigate your little obstacle course that you've made. My one's pretty easy, but maybe you can spend some time making a bigger one. Now, beyond any general gazebo issues that you might have, which I mentioned in the other tutorial, if you are having any trouble getting your robot to drive, just double check some of the parameters. So things like making sure you've got inertias set with reasonable masses on your wheels and on your chassis, making sure your friction value is right. You can try changing these torques and accelerations. That might make a difference for you. One thing to check is if you want to use ROS to topic echo, and we can echo the command velocities. Whoop. Then we can see when we send a command velocity, we can check that it's coming through, coming out of here at least, and then hopefully Gazebo is receiving it from there. Oh, and you also in this one want to definitely double check that your wheel separation and your wheel diameter are set correctly. So now that we've got the broad design of our robot figured out and we've got a functioning simulation environment, the next step is we're going to start looking at hardware. So in the next video, we're going to take a look at the brains of the robot. That's the Raspberry Pi. Now, if you're only doing these tutorials in the simulation environment and you're not building a physical robot, then there's going to be less for you in the next couple of videos, but I reckon you should watch them anyway. You might pick up something. And then the next time that we'll be back here in the simulation environment will be when we start to add sensors. So that's our LiDAR and our camera. Apart from that, as always, like and subscribe. If you've got any ideas or questions or comments, just let us know down below and I'll catch you next time.